both of these papers I'm going to be talking about today were co-authored with Lilia and Sergey Malyar. They were here at Hoover. I think they first came to Hoover as a visitors I sponsored back in the, I don't know, 2008, something like that. I forget exactly, or 2007. And then they stayed around for several years. Sergey now is a tenured professor at Santa Clara University, and Lilia is now a tenured professor at City University of New York. And obviously, Sergey is looking for jobs in the East Coast now. But anyway, both papers represent work, the major part of the work that they did with me while they were here in California. Now, both slides, by the way, were obviously done by them. The slides are somewhat, well, they're dated, but on the other hand, it's nothing that needs updating because this first set of slides is dated 2011, which was just before the paper, that paper came out in Quantitative Economics. So it represents an up-to-date version of what went on in that paper. Now, by the way, I'm going to be going lightning fast through some slides here because there's a lot of slides, and some of them are instructive on some details, but I don't expect you to, I don't mean to spend time on those details now. So within macroeconomics, there are three kinds of numerical methods that are used. Now, I spoke about projection methods. That was last Thursday, right? Yeah, last week. And that encompasses a wide range of methods. Perturbation methods, linearizing around the steady state, that kind of stuff. That stuff I will talk about on Thursday. I will note at this time that I'm switching the next two lectures. So perturbation will be Thursday, and then approximation 2 will be next week, Tuesday. So there's perturbation methods, and then there's a class of methods called stochastic simulation methods. Now, the stochastic simulation methods have certain advantages and certain disadvantages. Now, one of the problems with stochastic simulation methods is that you get to a point in the algorithm where you have to do a regression. However, the regression is horribly ill-conditioned, and so that limits what you can do with those methods. But now let's, now by the way, the example in the back of your mind should be the simple, basic stochastic growth model that we've seen, chatted about a bit in the past. Now, so this is a stochastic simulation method that does the following. You guess a policy function. Now, by policy function, I mean, suppose that there's the state variables are capital stock and also some productivity levels. And then you get your policy function is something that tells you how much you consume of each good, maybe includes prices, et cetera. But so you may have a vector of policy functions. And then given that policy, you then simulate the time series for consumption, capital stock, whatever. But now you then, with the simulated time series, you then check to see if the Euler equations hold. Remember, optimality in these, or equilibrium in these models, is defined by satisfying some set of Euler equations. So you guess a policy function, which is almost surely not a solution to the problem. You simulate it, you see what the implications are for that policy function, and then you look to see how bad the Euler equation errors are, and then you adjust your guess. And you go round and round and round until you have convergence. Now, in step 3, you use the simulation results to compute a different guess. What happens is that you end up having to fit a polynomial function to the simulated data. Okay, that's a regression. And by the way, these simulations tend to produce data sets that are highly collinear. So you're going to have a problem there. Now, the Euler equations also often involve conditional expectations, like marginal utility of consumption today is the expected marginal utility of consumption tomorrow times the marginal product capital tomorrow. So that means you have to do some integration. You have to compute the expectation somehow. Now, in the case of stochastic simulation methods, you have a multicollinearity in the regression, but then also what tends to happen is that they use Monte Carlo integration for the integrals, and so that's going to give them a very low accuracy for their integrals. Now, what we do now, basically, there are 2 canonical papers in the stochastic simulation literature. One is the parameterized expectations algorithm of Denhan, and then also later on Marcet. No, it's Marcet stuff, and then Denhan worked on some applications. And then also Tony Smith's thesis had a stochastic simulation approach also. Tony Smith's thesis is basically solving dynamic programming through a simulation method, but this is the more the solving equilibrium with these methods is the focus of Marcet's work, and that's what we're going to look at. Now, so here's the canonical simple problem. What we want to do is solve for the maximize expected discounted utility, and what happened here is that tomorrow's capital stock is the undepreciated capital stock plus gross output minus consumption. So that's one way to write it. Is consumption plus tomorrow's capital stock equals the surviving capital stock plus output. Then also there is a productivity shock, A, which is log normal. It's basically log normal. Now, and then you have some initial condition, K0 is given. And so here's your production function, consumption, depreciation, autocorrelation, anyway, standard kind of notation. Now, when you solve this out, when you look at the solution for problems like this, this is what the simulation produces. That basically your productivity level, remember, the productivity is exogenous. So your productivity levels are going to go up and down within this range. The capital stock is spread out. And you end up getting what is, some people may say cigar shape, but young people don't see cigars much at all. This looks like the Milky Way. It looks like a galaxy. It's a cluster of points stretched out, and then in the center it seems to be quite dense. So this is the kind of setup that you typically find yourself in. Now, by the way, you might say, well, the reason it looks that way is because of the scale. If I adjusted the scale on this graph, then I could get this to look like a circle, a disk. So, what does it? So saying that it looks like a galactic disk, that doesn't really say anything, because I could, change the scale and it would come out looking very different. Well, in fact, that's what we do. You see, suppose that you have units. Suppose your units suppose your units are such that when you plot productivity level against capital stock, you get a picture like this. And then you're trying to approximate the consumption function. Well, you're not going to want to approximate it over this whole region, because most of the region is never visited. The ergodic set is down here. And if you take a standard sort of projection method like I described in my lecture last week, and also is worked out in my JET paper, you're going to spend a lot of time trying to solve the Euler equation in regions that are never visited. So why bother with that? Now, the nice thing about simulation methods is that they're only going to solve the problem on domains where the problem visits. But now that shape could be, if their domain has that rectangular shape that we saw in the previous slide, you're going to be trying to solve the problem. Most of your effort is going to be solving the problem on regions where you don't care. So what we notice is that if we change the variables, linear change of variables, so that then that stretched out disk becomes a circle, and then in this domain with these units, we try to approximate the problem, then we see that galactic disk becomes a circle. And now then, if we try to approximate it on this domain, we're approximating it on, most of the effort is going to be on that domain. Now, in a three-dimensional case, okay, so basically the point of this picture is to say that, gee, here's the square and here's the disk. Now, if we know the problem is going to live in that disk, maybe we should focus on just solving it in that disk. Now, so that saves a bit, because the disk is only 79% of the area of the square, so that's a little savings. But now when you go to 3 dimensions, suppose your problem lives in a sphere or ball, and you have a choice between solving your problem on a hypercube or in that ball. Well, the hypercube has twice the volume of a cube of the same width. Now, in general, here's the ratio of area for a p-dimensional hypersphere and a p-dimensional hypercube. And in particular, when dimension is 10, the ratio is between the two is 3 times 10 to the minus. Basically, the hypercube is 300 times the volume of the hypersphere, and at 30, basically the hypersphere is an infinitesimal little tiny itty bitty part of the volume in the hypercube.
May I ask a clarification question?
Yes. Sure. Yes.
So so for example, for the ball graph here, right? So
yeah,
we're focusing on the ball because we're focusing on the steady state, and so the other points in the other areas outside of the ball.
We're focusing on the ergodic set.
Okay, so it's saying anything that appears in the steady state will in the ergodic distribution will be in the ball, but but anything else that's not in the ergodic distribution could happen. It's just that we don't care about them.
Yes, that's a very good point. In equilibrium, you're not going to get outside of this ball. So why why bother computing the solution out there? Now, there are cases in which it's interesting to look at. Suppose you start outside the ball.
Right.
And then you want to know how do you get into the ball? Well, now you then have to solve out for the problem outside the ball. But if you're just interested, as is typically the case in macro, you're just interested in finding the ergodic set and what the behavior is on that ergodic set, then you do this, you focus on this. Now, by the way, the other thing is that even if you are interested in a broader set of starting points, this is a good point to start with, because this is I corrected you when you used the word steady state, but this is a stochastic generalization of a steady state. So like in a deterministic problem, if you know the steady state, that helps you a lot in terms of understanding the dynamics around that. And that would be the case here too, is that if you know the dynamics within the ball, and you also know that the problem is dynamically stable, and that if you start outside the ball, you're going to go inside, then this is a good place to start. So yes, we're assuming.
Okay, so can we do transition dynamics though? Okay,
that's, you have to be very careful, let's say. You have to, whatever you do, you have to, let's save that question. But you know, you put your finger on the key problem here, or the key issue. If you're trying to do transitions, then you basically have to formulate the problem so that you have the both regimes modeled. So that's, anyway, I'll make sure I talk more directly about that later.
Okay, thank you.
Yeah. Okay, so the thing is that if you're trying, and this is the attraction of a stochastic simulation method, because it only really tries to solve the problem on the domain where the solution lives. And actually there was a conference in 2002 at Frankfurt Goethe University, and it was an interesting exchange between Wouter den Haan and myself. Wouter den Haan made the comment that, well, now we all do projection methods, as if discounting parameters expectations algorithms, we all do projection methods, he said. And then I said, any people who know the history knows that there's a certain lot of irony in all this. I said that, no, there's an idea in stochastic simulation methods that is very useful, idea of solving it on the domain where the problem lives. That's a key feature of stochastic simulation methods, parameter expectation, and there's something valuable in that idea. Now that was 2002, and then and the Molyers were at that conference, and then they came out to Hoover, and then we worked this out. This is kind of like a response to that exchange. Now, so projection methods operate on a hypercube, and life generally revolves around a ball. Now, by the way, some of you may be aware of the fact that there actually are orthogonal polynomials on balls. They exist, and they're used a lot in physics. I spent some time looking at that literature, and I decided that one, it would take me a long time to understand what was going on, and then even a longer time to formulate it in such a manner that I could teach economists how to use spherical orthogonal polynomials, hyperspheres, not hyperspheres. I basically disbanded that idea. And I think this is a better idea, because even though my picture I gave you said, oh, let's try to solve this in a ball, sometimes that ergodic set is not the same as a ball. It cannot be transformed into a ball. Suppose that the initial hyperset is more like a banana. Well, then you still want to make things more compact, but you don't get into necessarily a hypersphere. So this is, I think, a more general idea and a better idea than trying to do orthogonal polynomials on a ball. Now, let's see what this is. The parameterized expectation algorithm of Marset, 1988, which I think was, I don't know, this was the first paper. So here's the Euler equation. Margin utility of consumption today is beta times margin utility of consumption tomorrow times the gross marginal product of capital. So you see, if you have an extra, if you save today and have one extra unit of capital tomorrow, then that gives you 1 minus delta extra units of capital at the end of tomorrow's period, plus this marginal product. And so this is the Euler equation for that problem. And let's just write the right-hand side as psi of k sub t, a sub t. And what is b? Well, b, what I'm going to do is parameterize the psi function. So parameterize all of this as an exponential, this is the exponential of a linear function of the logs. So by the way, this simple thing all by itself ends up being like a Cobb-Douglas production function. But basically, it's the exponential of something, and this could be a quadratic polynomial or higher order polynomial. So that's something. Now, so now, what are we going to do? Let's rewrite the budget constraint. Tomorrow's capital stock is the post-depreciation capital stock plus gross output minus consumption. Well, consumption today is U prime inverse of this right-hand side. So now what we can do is, if we have some guess for these parameters, and then we have some initial capital stock and initial productivity level, then one can just simulate the whole KT-CT process. So given K0 and A0, then you compute what the output is, and then from this then you have a K0 and A0 here. You compute the psi and U prime inverse, that gives you C, and so then you keep, and that will give you KT plus 1, and then you just you continue to construct the simulation. Now then you construct a variable called Y here, which is the realized margin utility of consumption in the next period. Suppose you're at YT, suppose you're at time T, then this is the margin utility of consumption as realized in the simulation. This is the KT as realized in the simulation. So then YT is the right-hand side of the Euler equation as realized in the simulation. Now then, what you want, okay, then here's where you then say, well, this YT should equal this psi function. Now, so we're defining this is YT is defined to be the realized margin utility of next period's margin utility of consumption. Now, on average, that should be equal to the expected margin utility of consumption tomorrow. So if I got the B right, then we would have this relationship that the series of YT would equal the size plus noise. Well, that's not likely going to happen. So what we do is we're going to find basically some bias here. So what we do is we run a regression using the simulated data, YT, KT, AT, to come up with a new set of coefficients b hat. And then what we do is that b hat is used to adjust the coefficients. So let's say we started this with, in the jth iteration, with b super j, and then we got this b hat. Now, by the way, if we just plug that in for the next iteration, this is likely going to blow up. So you do a dampening of it, and that's your next set of coefficients. Now, this does work okay for basically linear polynomials. However, here's the problem. This is going to be a non-linear least squares problem. Non-linear least squares problems have solutions, but it may be hard to find them. There may be multiple local min to that least squares problem. And so it may be hard for your computer algorithms to even find one. And if it does find one, it may just be a local min. Also, these coefficients are going to bounce around a lot because of the randomness that's in the Monte Carlo simulation. And then even if it does converge, the resulting approximation is often not very good. Okay. Oh, okay. Okay. I'll have to follow up with Brian on that. It wouldn't surprise me. So anyway, the solutions, they do get solutions that are degree 2 polynomials, but after that, it just doesn't work because the nonlinear least squares are just too unstable. Oops, let me see. Numerical. What are the numerical problems? The problem is the ill conditioning in the least squares problem. Okay, this is also kind of a expensive nonlinear functional form. Now, so here I just talked about least squares. You can have problems where where x prime x inverse is also not easy to invert, and you have condition numbers that may be too high. And then these are the slides where Lilia and Sergey go through some issues in numerical stuff that you already see. Now, our first goal in this paper, the first goal is to stabilize what Marcet was doing. Stay with the simulation, stay with the regression step and the iteration. But what we're going to do is we're going to replace nonlinear least squares with other models, with other methods, and in particular, we're going to make the problem so that it's linear approximation. So what we're going to do is we're going to do the same simulation method. We're going to alter the nature of the equation we're solving so that we can do everything in terms of linear regression. But now linear regression can also be very ill-conditioned, again, because of simulation, the data set's going to be highly collinear. So then what we're going to do is we're going to use other approximation methods. See, what the simulation does is create a cloud of points. And so that then gives us a cloud of points, a cloud of, you can think of, you have the CTs and KTs on the XY axis, and then the YT is on the vertical axis. And what you're trying to do is find some function that goes through that cloud of points. And so what we're going to do is find that there are many, many regression-like methods that will be stable. In fact, the only method that is not stable is least squares. And this is an example of where economists, they know about least squares, nonlinear least squares, linear least squares, whatever. But this is a case where just using that limited set of tools really fails you. And that what you need to do is get acquainted with other methods of basically approximating a cloud of points with some easy functional form. Now, oh, by the way, the first thing we say is that we want to normalize the variables. So you first center everything, and then you scale it so that everything is all, everything's centered around a zero mean, and you have so basically you transform it into being a nice, something like a sphere. Now, we're going to do a variety of different approximation methods. Least squares using singular value decomposition, regularized least squares using Tikhonov regularization. This is also called ridge regression in economics. And then we're also going to talk about least squares SVD. You can see through the details there. Regularized least squares with Tikhonov, that means that the L2 penalty, you're trying to minimize least squares, that's this term, but you're also minimizing the L2 norm of the coefficients, which basically is what ridge regression is. But by the way, one problem we had is, well, in terms of exposition is, yes, we're doing ridge regression, but at first that sounds like we're doing something bad, because I remember in graduate school 41 years ago taking econometrics, where the professor introduced ridge regression and then immediately went on to say, oh, that was a bad idea because you can't do standard errors, you can't do inference. Well, we're not trying to do inference here. So we don't care about the failures of ridge regression in terms of doing inference. We don't care about that. We just want to find a nice simple function that fits the cloud of points. So some of these methods may look related to statistical things. They are, but we don't, the goal of identifying coefficients is there, but we don't care about any statistical inference. We're just trying to find a curve that goes through the cloud of points. And so this is, and basically what happens is that with Tikhonov regularization, x prime x inverse may be very ill conditioned and making x prime x inverse hard to compute. What you do is you just add a piece of the identity and you regularize it. Now this is the idea I had at first. I said, oh, okay, let's do the stochastic simulation stuff of Marcet. But instead of doing least squares, why don't we do least absolute deviations? So minimize the sum of absolute values. Now this becomes, and I think we've seen this before in the course, that this boils down to solving a linear programming problem. So with linear programming, you don't care about x transpose x. Now the thing is that you don't have a nice, least squares has nice cute formulas. That's one reason why economists are so obsessed with them. But it's a linear programming problem. So that's expressing it in a fashion that you can solve it is superior to having cute formulas that don't work. So then you find out that it's a least squares. Now this is LAD. It's a computational detail. Also, you can, if it's a linear programming problem, you can also look at the dual. Now also you could do a regularized LAD where you minimize the sum of absolute errors, and then also you put a penalty for having a B that has large. So you can do that, and you can do the regularization of the primal problem, dual, whatever, anyway. And now then there's also principal component is another method for doing regressions. So what happened is I said, hey, let's do the LAD approach. Now, why did I suggest that? Well, it's because I was starting to read about work. So we're talking about the years like 2005, 2006. I was starting to read about, I guess now the best way to describe it is I'll read about like lasso estimators, or also LAD estimate. Anyway, that various kinds of estimators that did rely on the L1 norm of the residuals. And so I said, hey, let's try that. Now, then what happened is I say, oh, that's kind of a nice idea. But then they decided to go into the math literature and they found all these other ones. And so that's why the paper has results for, I don't know, not quite a dozen, but several methods. Okay, now, oops. Okay, now with Marcet, what he did is to parameterize marginal utility policy function. And now this, and it's when you deal with it in this way, you're going to have nonlinearities. But anyway, so what we're going to do is we're going to parameterize the law of motion for the capital stock. We're not going to parameterize the marginal utility. By the way, Marcet and others make a big deal about, oh, they're parameterizing the marginal utility function. I don't find that to be at all important. If you're parameterizing margin utility, you're parameterizing the consumption function. What you're in need of is to find something that has a decent function to be used for parameterization. And that is certainly in one of Brian Wright's papers, where they had to deal with finding some representation of equilibrium, which meant that they had to approximate a smooth function, and so in that sense, this is similar to what Brian and Jeff Williams did. So the focus on parameterizing margin utility of consumption, I think, is misplaced. What you're trying to do is find some function that behaves decently. What we're going to do is look at the law of motion of the capital stock, which, by the way, is going to behave decently because capital stocks only move slowly. Now, how do we get a function? Well, see, look at this. This is the Euler equation. Margin utility consumption equals expected margin utility consumption more, et cetera. So what we do is we bring the margin utility consumption today, we bring it inside the expectation. And so then, okay. These fancy slides, kind of a slow response in them. Anyway, so bring that inside, and we basically end up with margin utility consumption tomorrow divided by margin utility consumption today. Well, that's the marginal rate of substitution approach. And so basically 1 equals beta times the margin utility consumption tomorrow divided by today's times tomorrow's return. So basically, this piece is okay. If the KT plus 1 was not there, then this would be 1 equals the expectation. Now what we're going to do, but we want a function, we want an expression involving KT plus 1, because we want to express KT plus 1 as a function of KT-AT. Well, what you do is just multiply both sides by KT plus 1. So KT plus 1 does equal the expectation of all this stuff times KT plus 1. Okay? So that's going to be our psi. This is going to be our psi function. Now, what's happening is that we're assuming KT plus 1 follows this law. So this KT plus 1 here is really the K of KT-AT that's plugged in here. So it is just a function of KT-AT and then the coefficients. Now then, okay, here's what are we going to use? We're going to do polynomials, but we're going to stay away from the ordinary polynomials because they're highly collinear. We use some Hermite polynomials because this is, they're more wiggly and they're not so correlated. Here's the production function, and then here's the specifications. Also, our accuracy is measured by the error in the marginal rate of substitution Euler equation. And so, okay. Basically, okay, it should be a slide here. See, basically what we do is we make a guess for B. We then simulate an AT-KT process, plug that in on the right-hand side here, and then regress KT plus 1 on this to get our new coefficients B. So this is the same as the Marset's parameters expectations algorithm. Once we have something expressed, we then take a set of coefficients, a guess for the set of coefficients of this. We then grind away a simulation, and then, well, the KT plus 1 path should equal this plus some noise, and so then we do a regression to see what coefficients of B would do that job. So anyway, that's so it's the same idea. And now, what are the results? Well, by the way, a lot of times people love 100% depreciation of capital stock because then you get a closed form solution here. So here's the mean error and then how much time it took. If you did ordinary least squares, basically did our change, then unnormalized, then you see what happens is you can get up to a second order degree polynomial approximation, but and you get pretty good, but you can't do third degree. That's because without normalizing the variables, the multicollinearity is too bad. Now we normalize the variables, and now see we can things go about the same speed, but then we do get a stable result for the degree 3 polynomial. Now we do unnormalized, but we used Hermite polynomials, and now we end up with extremely accurate solution done in 10 seconds. Now then, let's look at these other approaches: LS, SVD, LAD, PP. They all do very well. Regularized Tikhonov regularization with a tiny regularization parameter does pretty well. It's also pretty fast, like for the first and second one. Yeah. No, either way, all of these things are fast, but the relative speed is what's important. Now we do partial depreciation of capital stock, and if you do the standard approach, you end up finding that higher order, it's impossible to get a good approximation. As you increase the degree of polynomial approximation, you don't get any improvement. And why is that? Well, now we get, and now that we've stabilized, so now we've taken parameterized expectations algorithm, we've stabilized it. But now what we found is that it's hard to get it to do really tight accuracy. Now, basically what's going on is that what's going on in Marset's PEA is that he's essentially using implicitly Monte Carlo to do the integration. And so what we do is we say, well, when we have to do some integral, we do when we have to do a conditional expectation, we just use a quadrature rule. I'm not going to go through the details here, but basically the thing is that by using more and more Monte Carlo points doesn't help much. Using quadrature can help dramatically with the accuracy and the speed because you're using far fewer points. Now we also then do something with rare disasters, and that does a good job. Okay, let me see. We also then, we applied this to the multi-country model that we talked about in the JDC symposium on this. And then again, we get the same results that regularized least squares does a good job. And then, then this TSVD does even better. Anyway, so there's a whole zoo of methods in here. And now, by the way, notice that the paper does give the results for my idea, the LAD, the linear programming idea. Now, linear programming idea does horribly. Now, that doesn't mean I give up on that. All of this, by the way, if you go to their websites, you will find code to do all of these things. Their code is there. You can run it yourself. Now, the code is all in MATLAB. And I think for most of these methods, MATLAB is a fair language to use. When it comes to anything doing linear programming, however, you're going to be using the MATLAB linear programming toolbox, and I don't know how good that is in terms of speed. So that may be the case that LAD, the linear programming methods are actually pretty good if you use suitable software. Now, okay, this is a good time to stop if you have questions or comments at this time. Okay. Any questions, comments? Okay, let me take a little sip. Now, so we call that the GSSA, generalized generalized stochastic simulation algorithm. Now, and by the way, that meant we have examples of where it does an impressive job on high-dimensional problems. I recall that when they were running this, now by the way, the paper was published in 2011, so that must have been 2009, when they were running this, and they had access to, there was a server on my Mac box at the time, and so I would occasionally look at my Mac box while they were running stuff, and I would notice that when you ask what percentage of CPU was being used, it would say something like 800%, which basically meant that it was using all the available cores. So parallelization was being used. And I think parallelization of this could be used even to a greater degree if you explicitly did it and you were using a simulation method, using some other language like C or Python or whatever, something that you could parallelize explicitly. Because you see, the computationally intensive part of this method is generating the data for your simulations. Well, that is something that is embarrassingly parallelizable. You want to generate a whole bunch of simulation, generate data, or you just give a bunch of separate cores, different initial guesses, and different random variables, and you end up quickly with a whole set of data. Now, to Meng Li's question, suppose since I've done public finance, the example that comes to mind is changing taxes. So suppose you have a tax system, and then that means that you have it centered on some region, but the economy, the ergodic set is in some region. And then you change taxes. So that means now then that the ergodic set is going to move. Now, how would you deal with that? Well, one way to deal with that is that you have a policy function that you're trying to parameterize. And now you do your simulations that you want to do, but what you should do is throw in extra points. Throw in points in that outside of throw in starting points that are outside of the ergodic set under the new policy. So let's say the old policy said that you would be at capital stocks up here. The new policy says it's down here. Well, what you should throw in a lot of simulations that begin up here in the old regime, in the ergodic set of the old regime. So by adding simulations that begin in the old regime area, you're now covering a wider collection of points in the state space, and then the algorithm will be forced to do a good job simulating the problem up there. Does that answer your question, Meng Li? That you basically add simulations that begin basically in points that were in the ergodic set of the old regime.
Okay, I need to digest.
Yeah. So basically
Thank you.
And then by having simulations that do cover that regime, do cover those points, then you're going to get an approximation over that domain also. So the thing is that if you just let the simulation run randomly without guiding it, yeah, you're only going to get answers in the ergodic set. You're only going to have validity in the ergodic set. But what you can do is augment your data with simulations that involve these other points. And then that augmentation is going to give it data in regions not in the ergodic set, and then that will be used to help solve the problem. So that's how you can do this. Now, the next paper is a further development of these ideas. Now, the key thing here, you see, we're still, with GSSA, we're still doing some nonlinear least squares on the simulated set. The problem is that your set, the simulation set, is not, what you're using to fit the function is not a well-chosen set of points. But we're going to improve that now. We're going to now, okay. So, okay, EDS, epsilon distinguishable set. Now, what is that? I'll define epsilon distinguishable set and then explain why we use that term. This is going to be a global method. We're going to use it to solve a new Keynesian model with a zero lower bound. I believe this was the very first paper that could stably solve a model with a new Keynesian model with a zero lower bound. And then we're going to have some other applications. And what we're going to do is we're going to merge the ideas of projection methods with stochastic simulation. Now, key thing, epsilon distinguishable set is a set of points situated at least, oh, yeah, this is social distancing. We could call this a social distancing method. Because basically every point is at least epsilon from any other point. So that's, okay, so think social distancing. That's what epsilon distinguishable set is saying, okay, we're gonna have a set of points, but oh, they gotta be at least epsilon apart from each other. And then we're gonna improve things in other ways also. Now, here's the problem, okay. Suppose we have our model now. We've done our linear change of variables. So the solution, the ergodic set lives on this cloud of points, which is spheric, which is looks like a ball, a disk. Now you might say, oh, we've so far said, okay, well that's nice. We've normalized the variables and then we apply stable regression methods. You might think that we should be happy. No, I wasn't happy. I wasn't satisfied, let's say. I was happy, but not satisfied. Now, why don't I like this? Well, when you're applying a regression through this whole big cloud of points, what happens is that you have a few points out here on the rim, and you've got a whole dense set of points here. Now, what that's going to do is that when you do the least squares regression, it's going to put a whole lot of emphasis on making a good fit here. And so then, and if you aren't careful, it's going to dominate. It's going to sacrifice accuracy out here in order to get accuracy here. Now, by the way, this is why I think why one should always do an L infinity norm of your Euler equation errors to see how bad the Euler equation errors are out here as well as in here. But when it comes time to think about now, what points should I use? This is now an experimental design question. This is a subset of those points. And notice that they're all at least some epsilon apart from each other. So the idea here is to have simulations generate this cloud of points. So you're simulating x1 and x2, and you have this cloud of points in the two states, x1 and x2. And then I want to create a uniform subset of that. So what do? What I do is I go through these points. I randomly pick a point, and I keep that. And then I go pick I check out some other point. And if that next point is within epsilon of the first choice, I toss it out. I don't want it. It's too close. And so then I look at other points, and when I find something that's more than epsilon away from my first point, it's allowed in the club. So now you get a club of 0.1 and 0.2. And then now you check out other points and see if find another point where it's at least epsilon away from both of these. Then you have 3 points. Now this may seem very costly to do. It turns out that by using a basic, simple, obvious algorithm, if you have n total points and you want to have in the end m points here, the complexity is order m times n. So it's not n squared. It's not quadratic in the number of points here. It's basically proportional to the number of points here times the number here. So this, and probably even better than that. So this is very cheap to do. Now, so that's an epsilon distinguishable set. Now, I think they, by the way, this, I believe the code is now available. Now, why do we call it epsilon distinguishable? Well, I had this idea about tossing out things so that we get this other collection over here. Now, then at the same time, I was reading a book by a Russian mathematician named Temlyakov, and looking through it. By the way, when I say I read a book like by Temlyakov, it's like I maybe read the first chapter and then skimmed later stuff. But early on in the book, he discusses the definition of an epsilon distinguishable set. And I said, oh, that fits it. And also, nobody in economics has ever used the term epsilon distinguishable set. So good, no possible confusion. So that's where that term comes from. This is not an equidistributed set from the quasi-Monte Carlo literature, which is why I had to come up with another term. And fortunately, Temlyakov obliged me. And actually, after that, I actually went to a seminar by Temlyakov, even had an office hour with him, and then even had dinner with him. Afterwards, I was so happy that I left mathematics in the late 70s, because here was this guy, world-class mathematician. He was educated in Russia at a top place in Russia for math, and then left, and for a professorship at USC. Now, by the way, I'm not talking about University of Southern California. I'm talking about the University of South Carolina. And so I'm thinking, had I stayed in math, there's no way I could compete with a guy like that for a job, even at the University of South Carolina. And a Yankee like me would never think about going south for a job. Anyway, so the competition in math market is really tough. So now our class of problems is different than Krusell-Smith. I don't know. The thing is, this could be used to solve a Krusell-Smith problem. It could be done. It could be used. And then, okay. And then, okay, this is something cute that, okay. Sergey and Lily like that car stuff. You can read about it in the paper. Again, we have the same representative agent neoclassical model, growth model. Now, what are we going to do? Now, here I just describe what a projection method is, and of course, there's cursive dimensionality problems. And okay, so this is all standard boilerplate stuff. Okay, this is just, you see, they were giving this presentation at a macro conference, and so they have to sort of bring people up to speed on things. And this is a repeat of what you saw already. Now, okay, so we're going to merge projection and stochastic simulation. So what are we going to do? We're going to use simulation to create our data points, our sample. Then we're going to do something and normalize it. They say principal components. Anyway, they do some nonlinear change of variables or something to make it more like a sphere, more like a ball here. And then density, this is something I don't understand this step. And just forget about this step, because this is a step where I think they toss out some points at the edge. That shouldn't be done, I don't think, anyway. Now then, from this cloud we have, you construct the EDS, the epsilon distinguishable subset. And then what happens from this cloud, which could be like thousands of points, this is what we end up with. epsilon distinguishable set in the units defined by the principal components. Now, if we go back to the original data, then it's spread out like this. But this is the domain over which we're going to be doing our approximations. So now suppose that you simulate and you find out that your simulation has this galactic stuff, and then there's a wacko cube or square coming in here. This must be the Borg, I guess. And then you got all sorts of other points. Now they do epsilon distinguishable set, and then they throw out a lot of points. Now, by the way, frankly, I would leave in a lot of these points because if they are part of the domain, they should be kept in. Okay, that's just a disagreement between among co-authors. But anyway, you see the point. Basically, what happens is the epsilon distinguishable set gives you this set of points, which is a representation of this set, except for areas of very low frequency. And this is an example of why, in this example, I wouldn't want to transform it to do spherical polynomials. Now then, the other thing we do is, okay, so now what happens? We do the same polynomial approximation of the capital stock rule. We simulate. Here now theta, in this paper, theta is your productivity level. You simulate capital stock and productivity levels, and you do a big simulation. But when I say simulation here, I should make a distinction between two ways to do this. One way to do this is to do one single simulation that just starts with some initial capital stock and then just does a long simulation. Now that's going to model the ergodic set. But then but that may take a while. That, by the way, is something that doesn't exploit parallelization. Instead, what one should do is do mini simulations starting with a variety of different k's and thetas. And instead of having one long simulation of 1,000,000 periods, you do 100 simulations of 10,000 periods. And so that would be a lot faster if you have 100 cores. So that's a detail that's important depending on your applications. But anyway, after you do all your simulations, you construct your EDS grid. Now, we now have a set of points that we know is important for the problem. We also know that in some sense it's uniformly distributed, roughly uniformly distributed in the domain where the problem lives. Now we are kind of in the world that projection methods are made for. Because what does a projection method do? It says, okay, you know something, you pick a set of points, and then on that set of points, you impose some conditions on your Euler equations and your parameterization. So now that we have the equidistributed set, we now solve for the coefficients in some, given the capital and the theta, we can solve immediately by, actually in the one-dimensional case, just by if you know today's capital stock and today's productivity, and you have this for tomorrow's capital stock, you know what today's consumption is. And then what you do is you do monomial regression for this in this term where you have a conditional expectation in the Euler equation. You use this a quadrature formula for that, and now then you regress like these things on your K theta, and then you get new coefficients. This is now just basically, this is now, see, you could do any kind of projection thing here. What you're trying to do is you have a set of Euler equation errors, you have a policy function, and then what you want to do is at these nodes, you're trying to find some polynomials, coefficients, so that your projection conditions hold. And now this regression is just one example of doing those projection conditions. So see, now that we're down to a much smaller set of points, uniformly spread out, and now you can very quickly solve out for the a new guess for the coefficients. And so here is the various things. Basically, this is, I don't know why it takes, you might say, why does the second degree polynomial take less time than the first? The reason is that you use the first as an initial guess to do the second, and then that's an initial guess you feed in when you do the third degree, et cetera. And so the mean error, the L1 error is, by the way, this is log base 10. So this means you have 9-digit accuracy. The max point, the error at the max point was 8-digit off, 8-digit accuracy. And so you also talk about how to do the quadrature rule here. Now, what happens, you might not think this works, and this is, suppose your first guess has an ergodic distribution over here. Now you do a regression. Now what happens then that the next guess for the policy function actually has an ergodic distribution here, the third one is here, and the fourth one is here. Now this is kind of luck. This works. I don't have any deep insight as to why it works, but it does work. This is what you'd have to keep track of. And if the ergodic distribution of the different guesses starts to wander off in crazy directions, then you probably, you should dampen it more. And then now here's where we used, here we compare things on a projection method using a Smolyak grid. And what we find out is that EDS is as good. But that's again because you're doing a hypercube versus a ball. Okay, so here's a Bellman equation, representative agent, multi-country model. And we were able to solve like with 40 countries, but that's 40 countries. Each country had its own productivity parameter. So there's 80 dimensions. And we were able to get in 24 hours, get something to work that had 4-digit accuracy. Now, by the way, this would be 24 minutes if you had a decent computer. I think this is because you're using MATLAB. And also, by the way, this was on a computer. This is also on, I think this is also on my computer, my old computer. This could be much faster today. And then even, this is a 400-dimensional problem, and we got 4-digit accuracy on average. So anyway, these can solve higher dimensional problems. And then also supposedly the best selling point was to use this method to solve a problem with a zero lower bound. In macroeconomics, this is a big deal. Zero lower bound on the interest rate. And so we solved, this is a global solution method for zero lower bound. We had, 6 exogenous shocks and 2 endogenous state variables. So there's an 8-dimensional problem, Everything, and 8-dimensional problem. We discretized the exogenous dimensions. So we ended up with a whole big pile of 2-dimensional functions. So here's stochastic processes for various shocks I'm not going to go through the derivation of this because if you haven't seen it before, you're not going to get anything out of my whatever I can say in the next few minutes. But here's the key problem is that if the monetary authority is following a zero lower bound, that means that the gross interest rate is going to be at least 1, which means 0% interest rate, or this other formula. So that's a Taylor rule. So you're looking at an economy under a Taylor rule. And so here's a description of the problem. We impose, we ripped off some macro stuff. So here's simulation. And basically, we do a whole lot better than any of the methods that are used in macro. And what's nice here is that this is a time series. So this is a solution for our model when we allow interest rates to go negative. And so here you have, you're in Switzerland and German territory with negative interest rates. But now we impose the zero lower bound, and what you see is that, yes, we do get it right, that it's stuck down here. And it turns out that can have an effect on the economics. So this is, as I said in my email, I think this is and of all my macro work, this is the work in these 2 papers is the best macro work I've done. And I've done a lot of the perturbation stuff that you'll see more of. But in terms of potential generality, these methods have the greatest potential value. Now, there is a little thing about how I do not appear as an author in the published version of the EDS paper. The reason for that was I really didn't have a good choice. The editor demanded that we make some comments about the macro literature, which I knew were false. We're all supposed to make flatter his work, which I also was not happy with doing. I would not do that either. So basically, we had such a hard time getting this paper published. It went 3 rounds through Econometrica, and then at the end it got rejected. And then the editor said about the EDS paper, he says, I don't understand why you just don't do least squares, which means he had no understanding of the earlier paper, why we don't just do least squares, and really no understanding of anything in the EDS paper. So then we sent it to QE and then ran into an editor that demanded these things and also wanted us to say mathematical things which are false. Thing is, I knew they were false. I knew this stuff that he wanted us to say was crap, but I wasn't going to argue with him. It would just delay things too much, and we'd had too much delay. So I just said, take my name off. I'm not going to, we had enough of a fight. So anyway, so that as far as the official authorship is, I'm not an author, but you look in the footnote and you'll see that I was. Anyway, so those two, that body of work there, I think really it's certainly the best macro computational work I've ever been involved in. Now, it's not used much. I think the only application I'm aware of GSSA is work done by Yasmina Hajahodzic, a Larry Kotlikov student. She used it in a overlapping generations model. And otherwise, I don't know of any other applications of this stuff. Now, the one problem is that, what would be nice is to have software that people could easily use, could plug in their specifications for their problems, and then, easily organize things and then use the technology. That is not something that gets papers published for you. That's something that is not required of journals, is not rewarded at all in economics. And in fact, it's something that economists really don't want done. So, and will oppose and, nastily oppose efforts to create such software, which is something you'll hear more about soon. So, but that's the, now, so that's where things are right now. Like I said, I'm sure that this could be done to handle heterogeneous agents and new Keynesian models, because remember, we had some examples where we had 200 countries. By the way, these are 200 different countries with different utility functions, and different production functions. So basically, it's heterogeneity, probably in more heterogeneity than in these Hank models or heterogeneous agent models. So it's the business about how the heterogeneous agent models looks at a continuum of agents. Well, that's all baloney, because first thing they do is they find one way to make it effectively a finite number of agents. And I don't think, and by the way, this could easily solve problems with 1,000 heterogeneous agents also, with obvious modifications. So this could be a competitor to the Krusell-Smith approach. I'm not going to talk about the Krusell-Smith approach. I'm not going to bother telling you about it. I do suggest you look at the Kruger, and then there was some other guy, I forget, paper on Smolyak, methods of approximation, and they solve a problem with their method, and they get very, very low Euler equation errors. Then they solve it using Krusell-Smith, and you find out the Krusell-Smith model, the procedure generates is bad. Also, a paper of mine that came out about a year ago or so with Thomas Mertens, we also have an example of a Krusell-Smith approach to something, and then our approach and the Krusell-Smith approach is off, is not good. So basically, it's documented that the Krusell-Smith algorithm is not reliable. That doesn't, macroeconomists don't care about that. Krusell's on the Nobel Prize Committee many years, so and that's what everybody's goal is, so suck up to Pear is what you got to do. So anyway, so that's this particularly if this got on serious hardware, this stuff would outperform anything that's out there. The macroeconomists who rule economics do not want that to happen and actively prevent it. But anyway, so that's where we are in terms of these macro models of this kind. Any other comments or questions? By the way, the Euler equation stuff that we have here is also what goes on in any econ model, any model of commodity storage and movement or heterogeneous producers of an agricultural good or so. So basically these methods can also be used for that. And like I often say, I got first motivated to go to do these kinds of approaches to solve problems by looking at Brian and Jeff's early papers in '82 and '84. So all of this technology can be used in that literature also. So as well as public finance, this is all done for macro because that's people in macro are trying to solve these models and not doing a good job of it. So that's why we did focus on macro. Any other comments or questions?